in question number 4, we have to find the center of mass of a semicircular arc. So here is the semicircular arc, and it has uniformly distributed mass. So lambda is mass by length, and that is constant. Okay, so here the x-axis, the axis of symmetry, y-axis here, O is actually center of curvature of this arc. So from symmetry we can say that the y coordinate of the center of mass is equal to 0. So you have to find the x coordinate of center of mass. That is, the thing is, the arc is symmetric about the x-axis. So the center of mass lies on the x-axis itself, somewhere around here. Now, so we have to find x coordinate of CM. For that we take an angle theta. So this x-axis is the reference for measuring theta. So theta equal to 0. So theta is the angular position or the angular coordinate. It has got 0 here. So anti-clockwise angle positive and clockwise angle negative. Okay, so theta, and with theta a small angle d theta. So this part of the length is r d theta, r times d theta, radius of the arc multiplied by the angle subtended at the center of curvature. So now this has got mass dm, right? This r d theta, this part has mass dm. So we can write dm equal to lambda times r d theta, and the x coordinate, if you drop the perpendicular from here, you get the x coordinate, which is equal to r cos theta. Y coordinate is r sin theta, but that is not required. We know that the y coordinate will be 0. Okay. So for this dm, x coordinate is equal to r cos theta, and the total mass, what is the total mass? Total mass is equal to lambda multiplied by pi r. So xcm is equal to integration of x dm divided by m. So integration of x means r cos theta times dm means lambda r d theta divided by lambda pi r. So the limits of theta will be from minus pi by 2 to plus pi by 2. As if you have to cover the entire semicircular arc, so you have to split it into particles like this, right? If you have to split it into particles like this. So the limits of theta, the lower limit of theta is here, you see there, theta is equal to minus pi by 2, and there theta is equal to plus pi by 2. So it varies from minus pi by 2 to plus pi by 2. Then you cover the entire semicircular ring. Okay, so integration, so this, in this integration, this lambda will come outside, lambda radius, so you're left out with r divided by pi. So integral cos theta d theta from minus pi by 2 to plus pi by 2. So here we have r by pi, that's sin theta, from minus pi by 2 to plus pi by 2. So r by pi sin pi by 2 minus sine of minus pi by 2. So that is sin pi by 2 is 1, and sine of minus pi by 2 is minus 1. So you get 2 here. So 2r by pi. So xcm is equal to 2r by pi, and obviously ycm is equal to 0, because the this semicircular ring is symmetric about the x-axis. So in this problem it is an arc but not a semicircular arc. It subtends angle 2 phi at the center of curvature O. So we consider the x-axis through the line of x-axis symmetrically, so that the center of mass lies on the x-axis. So the arc is symmetrical about the x-axis. So there lies the CM on the x-axis. Now the method is actually same as we have done in the last problem, only the integration limits will vary. So that's d theta. So this is again r d theta. So here suppose say lambda is mass by length, we can assume, because it is distribution is such uniform distribution of mass. So lambda is mass by length, so total mass is equal to lambda times 2r phi, and this dm is equal to lambda times r d theta, and the x coordinate is equal to r cos theta, y coordinate is r sin theta, though we do not need this y coordinate because ycm will be 0 anyway. So xcm is integral of x dm r cos theta times lambda r d theta from minus phi to plus phi divided by lambda 2r phi. So if you put the limits, you get r by 2 phi sin theta minus phi to plus phi. So xcm is equal to r sin phi by phi. So actually the this problem number 4 is a special case of this problem number 5, right? Say if you put theta, if you put phi is equal to pi by 2 for a semicircular arc. That is what we have done in the previous problem. So here we have to locate the center of mass of the hemispherical shell. So uniform distribution of mass throughout the surface. So let's consider sigma is mass by mass per unit area. Okay, so here this is the 0, and this upward you have the y-axis. So actually, here we have to find out ycm, the y coordinate of the center of mass, while this xcm is equal to 0. From symmetry we know that if this is the x-axis, then xcm is equal to 0. Here we consider the elementary rings like this. So elementary rings, just I will show you how these rings are taken. They are this way. And this way, like this. Okay. Now, so the angle we take here, from here you consider an angle theta, and same way this small angle, this small angle d theta, so that this much length of the arc, this length of the arc will be r d theta. See now, this length is equal to r times d theta. Same way this length here, right? This length is r d theta. Okay. Now what about the radius of this ring? So you divide this shell into rings. So the radius of the ring is r cos theta, because if you drop this perpendicular, right? So this is going to be r cos theta. So what is the area of the ring? So area of the ring is 2 pi r cos theta multiplied by r d theta. So what is the mass of the ring? Mass of the ring, here mass of the ring I will take as dm is equal to sigma into 2 pi r cos theta r d theta, so that will be r square cos theta times d theta. And what about the y coordinate of the ring? So y coordinate of the ring, here you see y coordinate of the ring, distance of the center of the ring from O, that is r sin theta. So what's YCM? YCM is integration of y dm divided by m. Now what is m equal to? M is equal to sigma multiplied by the area of the hemispherical shell, that is 2 pi r square. So here the limits of theta, see here, so YCM, right? YCM is integral y dm by m as we have written. So y will be r sin theta, dm will be sigma 2 pi r cos theta times r d theta divided by m. M will be sigma 2 pi r square. So the limits of theta. So here see, you want to cover this entire shell. So how to cover this entire shell? You take ring after ring like this, right? Ring after ring like this, and then you make up this whole shell. So here, what is the limit of theta? So the limit of theta is from 0 to pi by 2, right? So there it is, so sigma 2 pi r cube, right? 1 2 3 2 pi r cube by sigma 2 pi r square integral sin theta cos theta times d theta. So there it is, you can write here sine of 2 theta. So from 0 to pi by 2, so here you have r by 2 integral, so this is cos 2 theta from 0 to pi by 2 minus sine minus cos 2 theta 0 to pi by 2. So r by 4, then cos 2 theta pi by 2 to 0, you can change the limits like this. So r by 4 cos 0 minus cos pi, so that becomes equal to r by 2. So YCM is equal to r by 2. That is the center of mass of for the hemispherical shell like this. Center of mass is located here. From the base, the height is half of the radius. So in this problem, you have to find the center of mass of the L-shaped rod as shown in the figure. Now, you see this, so it can be split up into two rods, right? See this one rod parallel to the y-axis, another rod parallel to the x-axis like this. So as you see, both rods will have same length and same mass also. So the upper rod has center of mass there at the point shown, and the x-axis rod has center of mass here. So suppose so m is mass of each rod. Sorry, mass of each rod. So m and m, that total mass total mass is 2m of this L-shaped rod. So actually what we have done, that we have replaced the rods by point masses at their center of mass. So this can be done for calculation of center of mass. See, so now in a new figure you have only these 2 point mass, m and m each. What are the distances? So L by 2, and this is also L by 2. And where is the center of mass of this? Obviously you can say here, say this is m1 and this is m2. So m1 is m and this m2 is m. So x1 is L by 2, y1 is 0. So here x2 is 0 and y2 is L by 2, because see, these are the coordinates. So L by 2 0, this is 0 comma L by 2. So xcm is m1 x1 plus m2 x2 by m1 plus m2. So that comes out to be L by 4. Similarly, ycm is also equal to L by 4. Okay. So these are the coordinates of the center of mass for the L-shaped rod. So this is here actually. See for this L-shaped rod, center of mass is here. So L by 4, right? There it is, center of mass. Or what you could have done here, once you replace by the point masses, so for 2 masses, what happens? Just join, see here, just join these 2 particles by a line, and obviously center of mass of the system will be at the midpoint. So there it is, center of mass. And obviously this, you know how much this distance will be, that is going to be L by 4, and also the y coordinate is going to be L by 4. This is an example of composite bodies. So whenever you have to calculate or find out position of the center of mass for composite bodies, then you can replace the bodies by point masses at their center of mass. For example, say you have a sphere and say a rectangle like this, as a sphere, or say a disc, say that's a disc, and this is a rectangular plate. So you have to look at center of mass. Suppose, so there lies x equal to 0 and this is the x-axis. Where is the center of mass? Find the x coordinate of the center of mass of this setup. Then you have to know the mass of the disc m1 and mass of the rectangular plate m2. Now this whole disc, just for calculating the center of mass, just forget about the disc, replace it by a point mass at the center of mass. And similarly for this rectangle, forget about the rectangle and consider a point mass m2, right? And if you know the corresponding distances, right, see it becomes so simple, right? See, x-axis, this is x equal to 0, this is, so all the bodies are replaced by point masses. So it becomes like calculation of center of mass of a discrete system. So simple as that. xm is m1 x1 plus m2 x2 divided by m1 plus m2. So there are some problems where the bodies have cavity and you have to find out location of the center of mass. Such an example is that here there is a circular disc and inside this disc there is a cavity here. So the radius of the disc is r, and obviously as you see radius of the disc is half of r, and you have mass in this area only. So this part is hollow. the inside of this smaller disk is hollow. This is it. So uh, this is the shaded part is a part with matter, and the hollow part is the black one. So you have to locate center of mass, and this point is x equal to 0, and that's the x-axis. Now this part with hollow is equivalent to this whole disk, and so this whole disk and a smaller part. I'll draw it. Yes. Whole disk plus the smaller part of radius r by 2, and this is the large disk of radius r. So this is how you split up this disk with the cavity into the whole disk plus one more disk. Now you do it like see, if you had a charged disk, suppose a disk with positive charge with a cavity, this we can decompose into a positively charged disk plus a negatively charged disk. This negatively charged disk has exactly same size as that of the cavity, and then you superpose. Then you actually superpose. That means you have this positive charge, and so on it you superpose the negative charge, so that you have the actual charged disk. Similarly, we can use this concept of negative mass, right? So that means suppose sigma is mass per unit area. Here sigma is mass per unit area. So the mass of the actual disk is how much? Sigma. So suppose this is mass m, this is m1, and this is m2. Okay, so what is m equal to? So m is equal to sigma pi r square minus pi r by 2 square. That is m is equal to sigma 3 pi r square by 4, right? Yeah. So what is m1 equal to? So m1 is sigma pi r square. So m2, this is a special concept we use for these cavity problems, that is negative mass. So that is minus of sigma into pi r square by 4. Now the x-axis stays where it is. So that is x-axis, this is a 0, and for this also this is x-axis and this is a 0, right? That is how you have to superpose. Now what is x1 now? So you know that this large disks, so the large bodies, for calculating center of mass you can consider the large bodies and shrink them to their center of mass having the same mass. So m1 is equal to this one, so x1 is equal to, so this whole body has center of mass here, so x1 is equal to 0. So what is x2 equal to? X2 is equal to r by 2. So we'll apply the formula xcm m1 x1 plus m2 x2 divided by m1 plus m2. So m1 sigma pi r square times 0 plus, so m2 will substitute minus pi r square by 4 into r by 2 divided by, so m1 plus m2 sigma pi r square minus sigma pi r square by 4. So m1 minus m2 is m, actually this m1 minus m2. So what is xcm equal to? Xcm is now equal to minus of sigma pi r cube by 8 divided by 3 by 4 sigma pi r square. So that is minus r by 6, right? So xcm is equal to minus r by 6. So that means for this body the center of mass is located here at, so I'll draw a new diagram here. So for this disc with the cavity, the center of mass is located here at this part is matter, so that distance of the center of mass is equal to r by 6. Now here you have to find or locate center of mass of the semicircular disc of radius r. We have done it for a semicircular ring. Now we are going to do for a semicircular disc. This radius is r. Now we can split it up into rings like this. We will make use of the ring because we know the location of the center of mass of the semicircular ring. Where is it? It is at 2r by pi. In an example we have showed that. So that is the ring. So I'll split it up. So actually this is our plan. So to make this disc, semicircular disc, we'll split it up into rings and add all these rings to get the disc. So this is small r and the thickness will be d of small r. So now let's concentrate on the ring. Actually, semicircular ring of radius r, thickness dr. Where is the center of mass of that? The center of mass is at 2 small r by pi, as we have calculated it before. 2 small r by pi, this is the location of center of mass. Now, so dm is mass of the ring, right, of thickness dr and radius r. So what is dm equal to? Say sigma, if sigma is mass by area, so sigma into pi r times dr, and the y coordinate. See, as you see, for composite bodies like this, say you add up sphere and plate or whatever. So here we are adding up, stacking up these rings, half rings. So we can shrink the ring to a point mass located at its center of mass that represents the ring. So here it is, center of mass of the ring. So for that, y is equal to 2r by pi. Now for calculating ycm for this semicircular disc, it is integral of y dm divided by total mass. So integral y means 2r by pi, dm means sigma pi r dr divided by sigma, how much it is, pi r square by 2. So the limits of a small r will be from small 0 to capital R. Now here what you get, integral of r squared dr, r cube by 3. So you get 4 here, 4r by 3 pi. So this ycm is equal to 4r by 3 pi. So you have to remember that if you have a semicircular disc like this, so there is the center of mass, and it is from the base, the distance of the center of mass is 4r by 3 pi. So this is a solid hemisphere of radius r, and you have to locate its center of mass. So the center of mass of solid hemisphere obviously lies on the y-axis, as we have shown the y-axis. Okay, now we divide this hemisphere, solid hemisphere, into shells, hemispherical shells of radius r and thickness dr each. So for the hemispherical shell, for this hemispherical shell drawn, for the shell of radius r and thickness dr, mass dm, mass is how much? Rho, where rho is mass per unit volume. Here it's a 3-dimensional body, so mass by volume, density, mass density is rho. So rho multiplied by 2 pi r square times dr, right? And what about the y coordinate of this? Y coordinate means this whole shell will be represented at its center of mass. So that is equal to r by 2. Now the mass of the solid hemisphere is how much? Mass of the solid hemisphere, capital M, is rho times 2/3 pi r cube. So YCM, we can write integral y dm divided by m. So integral of r by 2 times dm rho 2 pi r squared times dr. R varies from 0 to capital R, small r varies from 0 to capital R, divided by mass, so rho times 2/3 pi r cube. So here you have pi, so rho 2 pi divided by 2 integral of r cube dr from 0 to r divided by rho into 2 pi r cube by 3. So there you get YCM equal to 3r by 8. So if you calculate, you will get it 3r by 8. So in this problem, this is a disc of inner and outer radii, so r1 and r2 respectively, and say sigma is the mass per unit area, and that is constant. So you have to locate the center of mass, and you know from symmetry xcm is equal to 0, so we have to find YCM. So that's simple way as we have derived. So we can divide this thing into rings, semicircular rings of radius r and thickness dr, right? So for this ring, actually for the above semicircular ring here shown, for the ring of radius r and thickness dr, what is dm equal to? Dm is equal to sigma times pi r dr, that is area. So pi r dr is actually area of the ring, okay, and its y coordinate. Its y coordinate means it is represented by its center of mass. So that is equal to 2r by pi. Derivation is similar to what we have done for semicircular disk. Only the limits will change. So YCM is equal to integral of YDM divided by M. So here integral of 2r by pi into sigma pi r times dr. See, the limits will be from this. So R1 to R2, and here you have sigma pi R2 square minus R1 square. So here what you have after calculating. So actually 1 2 I have missed out. I have written this here, this 2, because the mass, the total mass is pi by 2 R2 square minus R1 square. Okay. So after integrating you get this. So there will be this 2 going upstairs. So YCM is equal, as you can calculate, YCM is 4 by 3 pi into R2 cube minus R1 cube divided by R2 square minus R1 square. Now special case. Now the special case for the semicircular disc. So R2 you put at R and R1 you put as 0, then you get YCM is equal to 4R by 3 pi. Now this same problem can be solved in a different way altogether. So this disc, you can use the principle of superposition here, as we have shown for this cavity. This is a problem with a body with a cavity, you can think like that. So if this is the mass, this part is having mass, okay. So this disc is equivalent to this whole disc minus how much? Minus or plus a disc of negative mass in place of the cavity. So that means say this is inner radius R1, outer radius R2. So this is the whole semicircular disc R2, this is the whole semicircular disc of R1. So here put M2 is equal to how much? Sigma into pi R2 square by 2. For M1 I'll put a minus sign, because this is supposed to be negative mass. If you superpose this, so this was the y-axis, right? So here y-axis, same y-axis was here. So it's minus sigma into pi R1 square by 2. Now what about y2? Y2 is 4R2 by 3 pi, and y1 is 4R1 by 3 pi. And as you know, YCM is M1Y1 plus M2Y2 by M1 plus M2. So you can put here minus sigma pi R1 square by 2 multiplied by 4R1 by 3 pi plus sigma pi R2 square by 2 multiplied by 4R2 by 3 pi divided by the mass. Divided by then sigma pi R2 square by 2 minus sigma pi R1 square by 2. So what you will get is same 4 by 3 pi R2 square minus R1 square, and on top you have R2 cube minus R1 cube. So you have two ways of solving. Either you can integrate, or you can consider this as a body with cavity. So here there is a triangular plate, and you have to locate the center of mass of this triangular plate. So this base, just so there is a base, and suppose the base is B and the height is H, and we have to find out the height of the center of mass from the base, right? So that's, so this is the y coordinate, right? Say there's a y coordinate, so we are finding the YCM. Okay. Now we divide this into plates like this, or rods rather. Divide the triangular plate into various several rods. So at a height y from the base, this is a rod of thickness dy, and say the length of the rod be equal to, say, L. Now, so the rod has thickness dy and length L, such that, now what will be the value of L? Now as the height is h, so we will use the similar triangle, that formula, so h minus y. So by similarity of triangles, so L divided by h minus y is equal to b divided by h. So therefore L is equal to b by h times h minus y. So now mass of the rod dm is equal to, here also it is surface mass per mass per unit area. So sigma is mass per unit area, mass by area, sigma into L into dy, right? And the y coordinate of center of mass of the rod is y itself. Okay. So see here, this is the center of mass of the rod. Right? So the whole rod you have to replace it by a point mass, same as that of the rod, but the point mass would be located at its center of mass. Okay, so what is the total mass? Total mass is sigma into area BH by 2, area of the triangle. So therefore YCM is equal to, there you downstairs you have sigma BH by 2, upstairs you have integral y dm, right? Dm is sigma L dy, so L replaced by b by h into h minus y times dy. So y will vary from 0 to h. So this you try out this calculation, the final result will be h by 3. That means the height of the center of mass is the height of the center of mass from the base is 1/3 of the altitude, right? So similarly, this is true for all the bases. So we can say that if you have a triangular plate like this, then if this is the center of mass of the plate, now say this height is h, say name this height is h, suppose, so that from this base height is h by 3. Now you can consider, say, another base, so this as the base, then the height will be h dash, suppose. Height means perpendicular distance of the vertex from the base. Then also symmetrically it will be same, the height, that distance, perpendicular distance of center of mass from the base will be h dash by 3. Similar for the other base also. This as the base, and suppose this is h double dash So the height of the center of mass from this base also will be h double dash by 3. Now for a hollow cone, you have to find out the location of center of mass. Now I'm going to do it in a very unconventional and tricky method. Generally, the method used to find center of mass of the cone is simple like this: divide the cone into rings and then integrate. So I will not do that. For here, I will try to make the cone by this. See, if I cut out from the slant surface of the cone, it will be a combination of triangles, right? Make this triangle so small that you can forget about this arc. This part is almost a straight line, so that's made up of triangles. These all, right? Now for each, that means instead of splitting the cone into rings, I prefer to split it into triangles, right? These triangles, if you join these triangles, this will form the slant surface of the cone. Now these are so small that these straight lines are so small angles theta, so that it is almost a round surface, right? So you can form the cone like this also. Now consider one such triangle here. Consider one such triangle. Now where is the center of mass of this triangular plate? Obviously it is 1/3 of the slant height from the base. If the slant height, because we have done just now this thing only, if this length is L, so center of mass of the triangle happens to be at 1/3 of L, right? Now if you look at the triangle just beside it, then where is the center of mass of this triangle? Obviously this is also at this 1/3 of the height from the base, slant height, right? So L by 3. Similarly, say this one, the triangle. So for this triangle, where is the center of mass located? Again at this 1/3. So all the triangles can be replaced by point mass. Point mass where? Point mass at their center of mass. So what you get actually is, this was the cone, right? Now that is the slant height of the cone L. So add this L by 3. This is what you get. Replace all these triangles by point masses. So you'll get a ring actually, right? See this point mass, like this. All these point masses are at distance 1/3 L. So this is 1/3 L, means this is 2L by 3. So obviously the center of the ring is at how much distance from the vertex? Obviously it is 2h by 3. So from the base, what is the distance? H by 3. So this is the center of mass of the hollow cone. The center of mass of the hollow cone is same as the center of mass of the ring. This is an easier method to solve the problem. Now this is a solid cone. I will tell you the result. The center of mass of this right circular solid cone is that will be at height h by 4 from the base. Okay. Now, this derivation I will not show you. There are two ways to split this cone, solid cone. You can try both the ways to solve the problem. One is divide this into discs, right? Like this, divide it into disc. And the other one is divided into hollow cones. So that can also be done. Divide this solid cone rather into hollow cones. And see, when you keep the hollow cones of variable thickness or variable size one on top of the other, starting from this cone here, so what you get after placing hollow cones one on top of the other, you get the solid cone. So either you can try by this method or you can try by this method. Okay, now this is a disc or a sector like a thing. So you have to locate its center of mass. Obviously, as the x-axis chosen, the center of mass is somewhere here, as the x-axis is a line of symmetry for this disc. So I'll show this by two ways. First, I'll divide this sector disc into rings. So this ring has say radius r and a thickness dr. So for this ring, what is the mass? dm is equal to say sigma is mass by area. So sigma times 2r phi times dr. And what is the x coordinate? Rather, the x coordinate of the center of mass of this ring is r sine phi by phi, as we know from the previous derivation. Now, what is the total mass of this disc? Total mass of the disc is sigma into half r square multiplied by the angle subtended, is 2 phi. So therefore the x coordinate x cm is equal to integral of x dm. X is r sine phi by phi, dm is sigma 2r phi times dr divided by sigma into r square phi. So here the limits of small r will be from 0 to capital R, because it's given, it's this radius of the disc is r. Okay, so after calculation, what do you get? xcm is equal to, so after calculation you get 2/3 r sine phi by phi. Now you can check it for the semicircular disc. For semicircular disc, what will be the value of phi? Yeah, 3 here, right? 3 here it is. So you know phi will be equal to pi by 2. Special case. And that result was 4r by 3 pi. We can verify that. So phi is equal to pi by 2. So this was x cm, right? Yeah, so x cm is equal to 2r sine pi by 2 divided by pi by 2 capital R, right? 2 capital R. So there you get xcm is equal to 4r by you have, so 4r by 3 pi. So that's verified. Now we'll try out by a different method. So the same problem of this sector type disc, so of radius r. So the alternate method I'm going to show it is like that. Instead of splitting it into rings, you can split it into triangles, and these are very thin strips like that we have done for the cone. So these are the triangles. Now let's take this let's take a triangle. Let's take this end triangle, right? So where is the center of mass of the triangle? Obviously the base, from the base, 1/3 of height from the base. So 1/3 of height from the base means it is, so r by 3. So that means from the center of curvature, that is 2r by 3. And so it is same for all the triangles, right? Say the triangle beside that, I color it green. So this triangle also is replaced by a point mass here. Similarly, all triangles are replaced by this point mass, dots, center of mass of these triangles. So if you join the dot, connect the dots, right, what you get is a ring. So actually what you have to find out now is there is a ring of which subtends angle 2 phi at the center of curvature, and which has radius 2r by 3. You have to locate center of mass of the ring. That is what the problem is. It comes down to this point. So you know what is this, right? What is this distance? So xcm for the disc is same as that of this xcm for this ring of radius 2r by 3. So you know xcm is, now for r sine phi by phi. So r, the radius is itself 2r by 3. So radius times sine phi divided by phi. So that means 2r sine phi by 3 phi. And this is the same result you have got.